Okay, so formal charges actually has to do with after you've drawn your final Lewis structure, you can go through atom by atom and assign a formal charge to it. And it's kind of a faux sort of thing, and you'll see what I mean. Okay, but formal charge is what it appears the charge, or the apparent charge, on a particular atom, okay, at what we call the nonpolar limit. The nonpolar, let's see, polar means the totally crazy polarness would be basically you have opposite charges. An ionic bond would be an example of something that's very polar. Okay, so the nonpolar limit is going to be where it's all about sharing, and I'll kind of show you what that means. Is that the real situation? No, but that's what we do to assess the formal charge of an atom. Okay, so the nonpolar limit, like I said, is assuming that, for instance, anytime you see a dash, we've been saying a dash means 2 electrons are being what? Shared, right? Okay, and we're going to assume that they're shared equally. Are they really shared equally? No. Okay, but we're going to assume they're shared equally. Okay, so anytime you see a dash, that's a pair of electrons that are in a bonding situation where that's sigma or pi bond, and we're assuming that they're shared equally. So I'll kind of show you what that looks like. So the nonpolar limit. What are the electrons at the nonpolar limit? And they're kind of fun once you do a few of them. It's almost easier to show you than to describe it. Okay. So it's a little subtraction problem, and it's got 2 terms. The first term you get off the periodic table. Okay, the first term, the number of valence electrons. We've been doing a lot of that. For group A, for group A elements, it's the group number, valence electrons. That's it. That's your first term. You okay? You look like he was yeah.
I've had a lot of congestion lately.
Oh, a lot of stuff going around. And from the periodic table number, you subtract this little calculation that you've done. In the setting that that particular atom is, you're going to assume all dashes are a pair of electrons and all pairs are split evenly between the atoms. Is that true? No, not necessarily. The other thing is if there's an atom that has a dot, lone pair electrons, it gets sole custody of those. Okay, so I'll kind of show you what that looks like. So it's a little subtraction problem. All lone pair electrons stay with their atom. All bond pairs, you split them equally. All right. So these are some general guidelines of formal charges. Most time you're going to do the little subtraction and you're going to come up with 0. So don't like, I got all zeros. Well, that's fine. Okay, there's no formal charges on any atoms. That's fine. Okay, especially if it's a neutral molecule. The closer your formal charge is to 0, the better. We talked about resonance structures, and the reason this kind of comes on the heels of resonance structures is if you assess your resonance structure and you come up with zeros as the formal charges for all atoms, that's better than if you have like a separation of charges. And I think I mentioned that. Okay. If you do have a separation of charges, formal charges, then your nonmetals, okay, or your, maybe they're all nonmetals, but remember your electronegativity increases from left to right, so it's most electronegative over here, and it increases from the bottom up. So you'd want your more electronegative atoms to be negative, okay, and your less electronegative atoms to be positive. So another thing is if you are dealing with a neutral structure and if you do have a separation of formal charges, they aren't all 0, then by golly, your formal charges need to add up to be equal to 0. And the example we're going to do here in a minute, that's the case. It's a neutral molecule. There is some separation, but they add up to be equal to 0. Kind of along those lines is if you are assessing atoms in a polyatomic ion, the Lewis structure of a polyatomic ion, and that the charge of that ion, that needs to be reflected in the total, the sum of the formal charges of all the atoms. Okay? All right. So, on for an example. Oh, anyway, so this is talking about the kind of the faux-ness of what we're doing here. You know, is it really, are electrons really shared equally? No, okay? But we're just kind of going along with this to assess the formal charge of an atom. All right, so this actually is the correct Lewis structure of nitric acid, HNO3. It's one resonance structure, I guess I should say. So everybody has complete octet. We have definitely divvied up all of the valence electrons, okay? So we can assess each of those, 5 atoms for what is their formal charge. We're going to go atom by atom. I'll start with the hydrogen. I'm going to kind of go from, I'm going to go to the terminal atoms first, then we'll talk about the 2 interior atoms. So that second number, not the first number, because the first number for hydrogen is also 1. But in this particular structure, do you see where hydrogen is just has a sigma bond to the oxygen? Pair of electrons, hydrogen gets 1, oxygen gets 1. Okay. We could go over here to this oxygen. This oxygen has 2 lone pair electrons. Okay. They're reflected right here and here, assuming we aren't kind of messing with the orientation. And these 2 electrons actually come from splitting these 4 electrons. See how that works? These 2 electrons came from, anytime you have a double bond, you have sigma pi, 2 plus 2, you have 4 electrons. Hydrogen gets 2, and we're going to give 2 to nitrogen. Okay, so we would say that the electrons at the nonpolar limit for oxygen is 6, for that oxygen. Let's look at that oxygen. Okay, so this oxygen up here, it had 3 lone pair electrons. They are represented here. Okay, and notice what's left over is that this guy right here is half of the 2 electrons part of that sigma bond. The other electron's going to go with the nitrogen. So we split it. Split it down the middle. So that leaves the oxygen and nitrogen. So the internal oxygen looks like this. So again, these electrons, okay, come along for the ride. Okay, this electron, I'll change to purple, came as half of this bond. Okay, and I'll change to green. This electron came as half of this bond. Does that work? So I got 2, 4, 5, 6. The only other one left is nitrogen. Nitrogen has no lone pair electrons, so it's all about sharing. So for that nitrogen atom, here we have 1 electron here, which is half of that. We have 2 electrons here, which is half of that. I'll switch to green. We have 1 electron here, which is half of that. See how that works? Okay. All right. So that's the second number in our little subtraction that we're going to do. So let's go ahead and calculate the formal charges for each of those five atoms. Okay, so hydrogen, it's 1A element. It has 1 valence electron minus 1 electron at the nonpolar limit. 1 minus 1 is 0. So again, if these all come to equal 0, then that just means it's a totally solid Lewis structure. Picking on this oxygen. Oxygen is a 6A. It has 6 valence electrons. In this particular setting, we're looking at 6 electrons at the nonpolar limit. 1, 2, 3, 4, 5, 6. So it's also 0. Like, oh my gosh, this is like a stoichiometry of 1 across the board. Pretty boring. Over here, again, for this oxygen, it's 6A. We have 6 valence electrons, minus 6 in this particular setting. That's 0. Finally something different. This north oxygen up here, okay, again, it's group 6A, so it's got 6 valence electrons. But in this setting, we're looking at 7 electrons at the nonpolar limit. So 6 minus 7 now is negative 1. Okay, so that's its formal charge. Last but not least, and since it's neutral, we're probably going to have a plus 1 on our nitrogen, aren't we? So let's just see. Nitrogen is a 5A element, so that's why that 5 is there, minus 4 electrons being shown here okay, at the nonpolar limit. So 5 minus 4 is a positive 1. Okay, so they weren't all 0, but doesn't mean this is a bad Lewis structure. The fact that they weren't very far from 0 is probably a good sign. The fact also that they add up to be equal to 0 is also a good sign, okay, because it's a neutral molecule. That's it. They're kind of fun. So we would write the formal charges then like this. The minus 1 up there and the plus 1 right there. So what's today, Monday? Friday, when we were in here, we looked at carbon dioxide, and the pot of valence electrons with those 3 atoms can be distributed like this one on the left or this one on the right. And most people think that the one on the left looks more symmetrical, it seems right. And we said actually this makes more sense because the expected valence of an oxygen atom is 2. Okay, it's group number 6, 8 minus 6 is 2, expected to form 2 sigma, total sigma pi bonds. Say, and so this one actually doesn't work. But let's go ahead and evaluate these both in terms of formal charges to see what we get just for kicks. So for the first one, I've gone ahead and kind of drawn circles around the 3 atoms. Okay, again, if what you're looking at here are the electrons at the nonpolar limit. Of course, these electrons are represented here. I'll change to purple. These 2 electrons are half of those 4 electrons, right? So we got 6 there. We actually have 6 over here for that oxygen. Carbon has no lone pair electrons, but carbon has half of these 4 electrons and half of these 4 electrons. So carbon has 4. So if we go to the periodic table, the oxygens are 6A, so they have 6 minus 6. Okay, so they're both 0, yeah. Carbon is 4A, so 4 from the periodic table minus 4 is what you see, that's 0. But over here, we got a different sort of situation. So over here, again, just like we did before with the nitric acid, we have, if we pick on this first left oxygen, these lone pair electrons came from these lone pair electrons, okay? This guy right here came from half of that bond, okay? So I got 7 over here. Carbon still has 4. That oxygen over there, this gets exciting here. Okay, these 3 came from half of that triple bond, because a triple bond is 2 plus 2 plus 2. A triple bond is 6 electrons. Half of 6 is 3. So that's where those came from. And of course, over here we have lone pair electrons. Okay, so we got 5 here at the nonpolar limit. So 5, and what do we say, 7 over here? All right, so bottom line is oxygen is a 6A element. So we're going to take what? 6 minus 7 for this one, and 6 minus 5 for this one. Okay, so that means the one on the left, this one, wait, did I say that right? Yeah, 6 minus 7. Okay, 6 is the valence electrons, minus 7 is what it's got here. That made it minus 1. So this guy is minus 1. And you're going to have some practice at this. And so, because that is, what did I say, 6, oops, sorry. Yeah, 6 is what the periodic table says, and it's got 7 there. Okay, over here, 6 is what the periodic table says, and it's got 5 here. Okay, so this guy is a plus 1. So again, if you're faced with having all formal charges of 0 or having formal charges of 0, minus 1, plus 1, the resonance structure with all zeros makes more sense. So these will be due, and like I said, I think they're kind of fun. This is the only assignment that's going to be due on Wednesday, unless you want to turn in some more labs. But The labs, to be fair, last day to turn them in, I guess would be your final, okay? But you don't want to wait till your final to turn them in. Okay, so let's take a peek at these. 10, 17. Okay, I don't have many hints for these. I did go ahead and for C, I kind of wrote it out, okay? So the C3, anytime you see this, this is actually what we call a methyl group, CH3, and it looks like this up here. So this CH3 is this CH3. And then we have a CH2, and then another CH3. Okay, so I just went ahead and expanded it out so you could get a sense for how it's laid out to go ahead and do what we just did with nitric acid. So basically for each one of those atoms, I would write it out too. I would go ahead and just draw the structure and then point to it what its formal charge is. So do that for A, B, and C. Let's see what other hints I have. I didn't have very many hints. See, for 47, it says, through appropriate Lewis structures, show that the phenomenon of resonance is involved in the nitrite ion. Nitrite is one of these you're supposed to have to memorize for Thursday's test. Okay, nitrite is NO2 with a -1 charge. My hint there in purple here is, well, I guess it's not a hint. Draw the Lewis structure of NO2 and show me that it has 2 resonance structures, at least 2. I think just 2. Okay. Resonance structure means that you've drawn your Lewis structure, and in lab we called it step 4. Step 4 means you've drawn your Lewis structure, but your middle atom doesn't have 8 electrons. So resonance structures most likely fall into this category. So you're going to pull a pair of lone pair electrons, you're going to swing it in so that atom keeps them, but they're no longer lone pair electrons. You're going to make a double bond. Okay, I've kind of shown it from this atom. Well, you could do it from this atom too, which also has a pair of lone pair electrons to potentially swing in and make a pi bond. So it depends on which atom you swing it from. Those give you 2 different structures. Those are called resonance structures. And then for 48, I just circled the word explain. Which of the following species requires a resonance hybrid for its Lewis structure? Again, I think you have to draw the Lewis structures in order to have them make sense. Okay, so you can't have too many Lewis structures. Oh, darn it. I left it on the printer, but I printed off for you guys because I'm like, well, how can I help them get ready for their test on Thursday? Why should I do it now? I haven't done all semester. No, I'm just kidding. But what I printed off was that that Unit 4 lecture guide. So is it before or at the end? I don't know. I would look at that darn thing as a list of things that are going to be on your test. Yeah, there's problems at the end. Yeah, it's the beginning. Okay. So I have a copy for it. I'll bring it on Wednesday. That's all, because I was looking at it, and anyway. Okay, so let's take a quick look at the next part that I said I wanted to do. That was looks like this. Sometimes I've even skipped this part. What the heck? This actually is just kind of a visual, more of a visual representation of what's going on with those pairs of electrons that are either in the primary bond or the pi bond, sigma or pi. So I don't have a lot more to add. Do you guys have blanks to fill in here? We could talk about the orbital hybridization for either one of the carbon atoms. It's symmetrical. And we would count sigma bonds, which there's 3, and we would count lone pair electrons, and this is kind of what we did in lab. I got sigma, 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 no lone pair electrons. So that's where I end up with sp2, orbital hybridization. And then from there, the other things fall into place. Okay, so that's the geometry around the carbon atom. This is the same compound. we talked about, and actually it's listed there in your Unit 4 lecture guide, which is the beginning of all the lecture slides. One of the things we talked about was bond length and bond strength. Okay, so double bonds, assuming they're connecting the same atoms, are stronger than single bonds, and they're also shorter.
Will there be any questions on bond length on the test?
I won't ask you, for instance, what's the bond length in ethylene between the two carbon atoms, but I might ask you,
Which one's longer?
yeah,
Okay.
definitely. Yep. I might, did you hear, you said, Mike, can you ask me which one's longer or shorter? And the answer to that is yes. Okay. The purple there are the 3 hybridized orbitals that carbon atom has undergone, created. The sp2 hybridized orbitals ready for overlap. In one case with its buddy carbon, and in other cases with the 2 hydrogen atoms. Okay. And here we see the purple hybridized orbitals overlapping with the hybridized orbitals from the other carbon atom and the non-hybridized orbitals from the hydrogen atoms. So there is the molecule. Here's some other representations of the molecule. I think what's emphasized here, since that's a double bond between those 2 carbon atoms, we have sigma, which actually connects the 2 nuclei of the carbon atoms, and then we have those 2 electrons that are in the region outside. Remember, I kind of brought that model the other day that had purple and pink. Okay, and then these kind of still images of the same thing, blah, 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 blah. Sorry. That one looks like a sandwich. So what you're seeing there, the black things are the carbon atoms. The white things are the hydrogen atoms. The white sticks are the sigma bonds, and that blue-purple is the 1 pi bond. Okay, a pair of electrons doing that. Blah, blah, blah. I think this is interesting. This actually, again, is the same compound. So this is sigma, 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 and these 2 make a single pi. Kind of interesting. Same thing, same thing. Like, really? Are you serious? We'll be talking a little bit about how you name organic compounds, a little bit in general chemistry too. But if you have the E-N-E suffix, that means you have a double bond in its most simplest form. Dum dum. I think these are silly. Okay. So acetylene now has the carbons bonded to each other, but instead of having 2 hydrogens, there's just 1 hydrogen on either carbon. So that we have a triple bond between the 2 carbon atoms. Be shorter and stronger, wouldn't it? If we were to ask or be asked what is the orbital hybridization for either one of these carbon atoms, we would count sigma bonds, sigma, and we have sigma. These other 2 are pi. So I'd come up with 2 hybridized orbitals. Okay, so that must mean it's sp orbital hybridized, linear, bond angle 180.
So let's say H was pointed to the, let's say if you line up a compass on there, if H was pointed to the northwest.
Northwest, like over here,
Yeah. How does that change it?
instead of here.
Is that just kind of like a
That's just kind of an alternate
alternate?
drawing,
Okay.
so, depiction.
Okay.
So that
If they drew
is,
it like that on the test.
that'd be fine.
Okay.
Yeah,
That's
yeah.
what I've been a little bit confused about.
Yeah, it's the same, whatever trajectory you spit it off from. It
Okay.
really doesn't matter.
Okay.
What if you put 2 of the H's on 1 carbon?
If you put like carbon, carbon, hydrogen, hydrogen like that,
Yeah.
is that a resonance structure? The,
You have to have,
well, to answer your question, the exam that you're gonna take Thursday, you won't be faced with this. I won't set you up for how do I arrange these. Other than when you arrange them, there's gonna be a central atom and then atoms coming off of that. So I wouldn't give you this molecule. But it's always gonna be something in the center and the lowest electronegative thing in the center and the other things coming off. because there's all sorts of reasons that that doesn't make sense. Just, you know, if you kind of kick things around, that doesn't make sense. So, but you won't be faced with that on Friday's test, or Thursday's test. You might down the road if you stay in chemistry. So here's the same structure. That bond angle, since it's SP hybridized, that bond angle is 180. And this is a shorter and stronger bond than was the carbon, double bond carbon. Okay. So this is showing the two hybridized orbitals in blue here. The linearness. I just think it doesn't do it for me much, okay? So, okay. So, if you would, skip past those problems at the end of the unit, which I think are awesome. And we will have a review, or not a review session, but it's our normal study session Wednesday, in case you have any questions, especially about those. But in the meantime, I want to do a few slides. Won't get to an assignment slide to talk about gases. How many people in here covered gases in their other general chemistry class? Or, yeah, gases like in high school, in biomolecular.
Can I just ask one quick question about that kind of stuff that's on the, this will be our last study session, won't it? Because then the next week is the
No.
final?
No, we'll have one more study session. Next week we have actually normal lecture.
Okay.
Next week, so this week you have your test on the
Okay.
8th, and then we have lecture on the 9th, and then we have normal lecture Monday, Wednesday. We even have a lab on Thursday.
Okay.
And then you hit your comprehensive final
Getting ahead of
the following
myself.
Thursday. Or, wait, we haven't have a lab on Thursday, you hit your comprehensive final that following Friday.
That same week and the week after?
Um, Yeah, same week, yeah, there's no dead days. And what dead days, talk to somebody above my pay grade, no, I know.
So next week is our last week. Then we have the final next Friday.
And we have our final thing.
Yeah.
So we have test Thursday? No.
No.
Yeah,
We have a test
lab.
this Thursday, and the
Thursday.
final next
Final.
Friday.
Yeah. I think we're all saying the same thing.
So here we are, Monday, Wednesday, Thursday, Friday.
Friday the 15th,
So this is today.
Today.
We have lecture. I'm gonna put you for exam,
Okay.
And that's only
okay, lecture. And then the next week, we have lecture, lab, and then we have final.
Okay.
And that lab will be due.
Yes, and this lab will be due, if you come to lab, this lab will be due with just the calculations, yeah.
Now, this is more reason for me not to go to lab. It's not even
But she said that some of the calculations from that
I didn't say that.
lab might.
We'll be on
Something similar.
If we were grading on a curve, I'd say, don't bother, that's okay, you don't have
All
to.
right. Okay, that. And so along this line, today, we're just gonna introduce gases. I'll put G for gases. And so we have gases lecture here. We have gases lecture here. And our lab, of course, guess what? It's related to gases. Okay? And if I were to put dates here, what would we say this is the 8th, and this is the 9th, and then 9 plus 7 is, okay. So that's kind of what we got going on. Okay? Any questions? If you're a visual person, yeah. Okay. Yay, I love gases. Okay. So, we talked when you think about gases, think hopefully, well, you can think a lot of things, but, if I have these boxes here, going from left to right, solid, liquid, gas. And it's when matter in its gaseous state that it has all of this space between the particles, and they have all of this, if an arrow indicates motion, they have all of this motion. I love gases. They have a mind of their own, okay? So gases, you can compress them, and the cool thing is if you pressurize them, actually you can get them to change their phase. We know if you cool a gas down, it will liquefy. If you cool a liquid down, it will solidify. But also, and this we're going to talk about in Gen Chem too, there's the pressure element to changing phases too. So you can just apply pressure, and you can apply pressure, it stays a gas, but you can also apply pressure to make it liquefy. Those tanks of compressed air, you ever shut them before? Okay. Anyway, the other thing about gases is the bigger the container you give them, they'll take any container. They're like a dog, okay? It's like, oh my gosh. If you give your dog a little pen, okay, if you give your dog a big pen, they are totally like dogs, okay? I don't know if this is like dogs or not, but kind of related to its compressibility and taking on the volume of the container you give it. I mean, we talked about density. Density is how compact something is or how fluffy something is. So if it's expanding or kind of being compressed, you're changing the densities. So the density of gases are all over the place. They're very, in order to describe the density of a gas, you need to give some information, pressure and temperature most notably. They're pretty fluffy compared to their liquid and solid counterpart. Gases, like dogs, want to mix it up, okay? I've only been to a dog park a couple of times, but take your dog to a dog park, and what's he do? He visits, okay? So they want to make a mixture. Now, I don't think your dogs do this necessarily, but gases, because they have a lot of motion, okay, that motion actually, I think of them as wanting to escape. That would be like a dog. That's like a dog. Okay, and so in doing so, they actually create a banging pressure on the container that's holding them. And we're going to talk more about that pressure momentarily. So if my arms are the container holding the gas particles, okay, picture the gas particles just like knocking at my arms, trying to get out. So pressure. So Wednesday we'll talk more about this, but and I'm going to go ahead and draw my 3D box. I am terrible at 3D boxes. Maybe I should try to get better. Okay, but there's my box. Okay, and here's my little gas particles in there. Okay, I'll go ahead and show the kind of trajectory or motion of one of the 4 particles. But in order to, I can fully describe that gas, and I think this is so cool. I don't have to say what that gas is. It can be oxygen, it can be carbon dioxide, it can be argon, you know, it can be water vapor, okay? But all we need to do is describe the pressure that it's banging against its container, the temperature at which those little particles are running around, the volume that's containing the particles, and the number of moles, and we're going to introduce the variable N, in case you haven't used that before. N is the number of moles. So those 4 quantities, aside from the identity of the gas, I just think it's so cool. We'll talk more about that. P, V, T, and N. So I want to talk a little bit about pressure. Pressure is force divided by the area over which that force is being applied. Okay? Pressure is force divided by area. We'll talk about the pressure units for a gas. But just to kind of emphasize the whole force divided by the area over which that force is applied, here we have the couple of cylinders, the green and the pink, and they both weigh the same. And actually, what something weighs is a force. What something weighs is basically that object is creating a force due to its pull of gravity. Okay, it's gravitational attraction to the center of the earth. Okay, so these both have the same force going down, but check out where they intersect with the table. So here we have force, and here we have force. We'll try to make them the same length. But the area is different. So this area is smaller, and this is a larger area. Okay, so if pressure Pressure is force divided by area. Does this make sense? If we have a larger area, what will the pressure be? Greater or less? Increase the area. Increase the denominator.
Force would be, small.
The force is the same,
Areas where there's still be less pressure.
so the pressure is less. Yep.
Oh, you're right.
Force over a greater area.
Yeah, distribute the force over a greater area. That's actually less pressure. Less pressure per little area unit. So P is less. So P is more. Sound like a commercial. Okay, so pressure is force divided by area over which that force is being applied. They call it distribute the force over a larger area, having less pressure. So force is mass times acceleration. And actually that kind of gets to the reason things weigh anything is the acceleration due to gravity. And that acceleration is acting on a particular mass of the object. Now this is a lot of blah, 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 and honestly, it's just kind of background information because I just want to get to my pressure units or your pressure units of gases. So the Pascal is an elementary unit within the metric system of pressure. Pascal by definition is equal to 1 Newton of force per area of 1 square meter. So I don't have a yardstick, but 1 square meter. Well, the pascals, I mentioned that, but we aren't even going to be dealing much with pascals in chemistry gas problems. So we need to kind of get to the pressure units we will be dealing with. Before we do that, here are some pressure units. Let's see. We'll deal with, I'll circle the ones we'll be dealing with. You might already know this. We do some with atmospheres of pressure. We do some with millimeters of mercury. Of course, millimeters is like, you know, a length, and I'll talk about how do you get from length to pressure here in a minute. So those two. This one down here, if you fill up your tire, it's probably in PSI. If you fill up your tire, like 65 PSI is kind of what your tire needs to run. I don't know. Mine does, I think. PSI stands for pounds per square inch. That's PSI. Force per area. Okay, so those two. I guess maybe the other one might be a torr, maybe a bar. So we have some exact relationships up here. Actually, this between the atmosphere and millimeter of mercury, that equivalency of 760, 1 atmosphere is exactly equal to 760 millimeters of mercury. I'll go ahead and throw a 3-way equality up here. I don't like those, but is equal to 760 torr. Okay, and you can get that because the millimeter of mercury and torr are exactly equal. So kind of get that in the back of your head. I don't know, for whatever reason, I think the table that we use in lab a week from Thursday has units of torr. Maybe bars. All right. So the fact that each of these 4 columns of liquid all come to the same elevation up there just means that they are all exerting the same pressure, concept of liquid pressure. So 1 atmosphere is exactly equal to 760 millimeters of mercury. So mercury, of course, is one of the few elements that are in its liquid state under normal atmospheric temperatures and pressures. And so here we have a mercury barometer, and this is how we get millimeters of mercury as a pressure. So we have an open, this tube right here is closed at the top and it's open at the bottom. So mercury can flow in and out of that glass tube. And it will flow in and out of that glass tube related to the pressure that is exerted on that pan of liquid mercury. So the millimeters of mercury go like this. Basically, If you have more pressure, it's going to shove the liquid up more, and this millimeters of mercury is going to be greater up the column. So that's how that works. This is showing you the same thing. This actually is kind of showing you a few things. I don't know if you can see A. What's wrong with the top of A? It's open, yeah. So that wouldn't make a very good mercury barometer. Okay, so now we went ahead and closed it. Okay, notice that between B and C, the only difference is it's closed at the top, but C has a little more extra room to rise. Assuming it's the same pressure on those open pans of liquid mercury, did it rise anymore? Mm-mm. And the difference here, what's wrong with D? It's not tall enough to let it go up. Exactly. So this is kind of a neat little gizmo. We don't use these, or don't have to use them in any of the labs that we do. But this is a open-ended manometer. Make sure I get that right. So you can see the open end over here on the left, right? Glass tubing. Now this, the kind of, it looks, I don't know if it looks silvery to you, but this right here, this is liquid mercury. And the cool thing about that liquid mercury is it can slosh around. Now, the fact that this level over here is open to the environment, that actually is what we call the environmental pressure or the barometric pressure. The fact that this is level, these two are level, okay, it simply means that that gas pressure in there must be equal to your atmospheric pressure, because it's not sloshing it up and it's not going this way. It's equal. Now, the other thing, do you guys remember you did burettes? Okay, you did some titrations. And with your titrations, you had that stopcock. So I want to think stopcocks are always like this. Notice that that stopcock is parallel with the glass. That means it's wide open. That's important too. You could close it if you wanted to, but that in case you'd have like your gas in there and be totally isolated from your little mammometer. Okay, so it's open. So with all of that in mind, notice what the mercury's done now. The mercury has sloshed over to be higher over here. Why? Because you have a higher pressure now in your flask with a sample in it than is the pressure of the environment or the barometric pressure. Okay. How much higher is it in your flask than the barometer? Well, all you need to do is see what we call the change in height. Okay, actually how much it's sloshed over is your pressure difference, your delta P. So this case, higher pressure in the flask. This case, a lower pressure in the flask. Can you see why?
It's inverted.
Yep, it's sloshed over here. I kind of almost think of it as, you know, we have a lower pressure in here than we do as an environmental pressure. How much lower? Again, we can see how much it's sloshed over. The change in height is directly proportional to the difference in pressures, the delta P's, those two scenarios. That sort of thing, I want to say, we'll cover a little bit more in Chem 2, but a little bit this week.
Now, is that measuring pressure in the gas or the pressure of the environment? It's the pressure of the gas in the bulb.
It's the pressure of the gas relative to the atmosphere,
Okay.
the environment, yeah. So
hopefully
we
it's all
can
the same on
actually-
the outside to see the difference there.
And in our lab on Thursday, we're actually I'm gonna go to a website and see what the pressure of the environment is, and we're actually gonna use that to our benefit as part of our calculations, so. Okay, that was my little sign here, stop here, go no further.
You got as far as you wanted.